Alright, welcome back. This is the Tutor Wizard. Please subscribe right here. What we're doing is Math 15, Calculus 2. We're doing Lab 2, which is Transcendental functions and their inverses. Today's lab discussion is going to be essentially the three main types of transcendental functions: the trigonometric functions, the exponential functions, and the hyperbolic functions. Inside there, in this lab, I'm going to just focus on sine and cosine and tangent, not the secant, cosecant, and cotangent, but we'll do this in another video or some other time. And then what we're going to do is we'll discuss the inverses, again focusing on sine and cosine and tan in the categories of the inverses of the transcendental functions. And then we will do some properties and identities along the way for specifically logarithm laws, exponential laws, and then some trigonometric and hyperbolic identities that will help us in integrating a bunch of these types of functions. Let's get to it. Right, Kitty? Yeah. Alright, so first up we've got the trigonometric functions and their inverses. And again, I'm going to focus on sine, cosine, and tangent and their inverses: arcsine, arccos, and arctangent. You can use sine minus 1, cos minus 1, and tan minus 1 also, but I like these ones to distinguish from the hyperbolic functions. And hyperbolic, I'll use the minus 1 symbol. And for the exponential functions, we'll have a name, a logarithm. Okay, Kitty, go. Alright, the first function is sine x. Sine and cosine are obviously not one-to-one, neither is tan. None of these functions are one-to-one on their domains. So what we do is we restrict to an interval where they are one-to-one. On the interval negative pi over 2 to pi over 2, sine of x is one-to-one. Therefore, it has an inverse, arcsine, which is going to have these nice cancellation properties. You can only cancel sine and arcsine. So basically what it says is you can cancel them off if and only if you're going to do sine of arcsine, we have to have that x is in the range negative 1 to 1. If we're going to cancel arcsine and sine, to cancel to just leave x, you have to be careful with these. I'll do an example in a second, but you have to have where these guys, the x value is in between negative pi over 2 and 2 pi over 2. Similarly for cosine and tangent, the cancellation laws only work where if they give you a value, if the x is actually some value that they're going to give you, you can only cancel them if x is in the values of the domain of sine and arcsine, cos and arccos, and tan and arctangent, respectively. Let's do an example of this cancellation property. All right, so example 1, let's compute arcsine of sine of pi over 6 and arcsine and sine of 5 pi over 6. Pi over 6 is in the domain, so this one we're going to have is equal to just pi over 6, which essentially means they cancel each other. When can you do that? Since pi over 6 is inside negative pi over 2 to pi over 2. Let's see, 2, okay, 2. For the second one, we can't just say that this is 5 pi over 6. We can't just say that this is 5 pi over 6 because since 5 pi over 6, okay, Kitty, go, is not in negative pi over 2 to pi over 2. I don't know why those want to be 6s so bad. So what do we do with this instead? First of all, sine of 5 pi over 6 equals what? We can look at this and say, here's 5 pi over 6. We're in quadrant 2. Sine is positive in quadrant 2. And sine of pi over 6 is going to be 1/2. Therefore, we get that arcsine of sine of 5 pi over 6 is equal to arcsine of 1/2. And now we can say arcsine of 1/2 equals x if and only if sine of x, using the definition of what inverse is, equals 1/2. And so when does that happen? That happens at pi over 6 is when we're going to get root 3 over 2 1/2 for sine. And so this says that x is pi over 6, or arcsine of sine of 5 pi over 6 is equal to pi over 6. You can't just cancel unless the value is in the respective domains. Okay, let's do the next one. All right, for the exponential functions and their inverses, the logarithms, we're going to have for a strictly larger than 1, you can have, if it's 1/2, it'll come down like this one, or a to the negative 2 to the negative x will be coming down this way. But for all intents and purposes, this is a to the x. We can see that it's monotonically increasing and therefore 1 to 1, but algebraically we can't solve for the inverse. So what we do instead is call it logarithm. So the inverse is, notice that it's also the reflection about the line y equals x. If I have the line y equals x, then the graph of log ax is obtained by reflecting a to the x across the line y equals x. And we have the function a to the x is going from r, but it is never negative and it is never 0, so its range is 0 to infinity. Therefore, the logarithm function has a domain 0 to infinity and a range of all the real numbers. Also notice that that says that the limit as x approaches infinity of log ax is infinity, and the limit as x approaches 0 from above of log ax is negative infinity from these two limits, and we have similar limits for these guys, which you should meditate on. Also, it should be pointed out that this is the cancellation laws for exponential functions and their logarithms. You can cancel these two guys if x is a positive number, and you can cancel log ax and a to the x if x is any real number. These are the cancellation laws for the exponential and logarithmic functions. Let's now do the exponential properties and the logarithm laws. All right, for the exponent laws and the logarithm laws, I've written down the 4 most important useful ones anyways, but we have if we add in the exponent, that's the same as multiplying in the base, as they say. So a to the x plus y is a to the x times a to the y. I've actually checked that one for the 2's down here. If I have 2 to the 2 plus 3, that's 2 to the 5, which is 32. And if I do 2 to the 2 times 2 to the 3, that's 4 times 8, which is also 32. That works out. Similarly, if I subtract, this will be division in the bases. And we can, if we have multiplication in the exponent, we can separate that out in either way. This will be useful in certain tricks when we do trigonometric substitutions or trigonometric integrals, for instance. And this also says that we can distribute the exponent onto 2 different bases. For the logarithms, if we add on the outside of logarithms, this is the same as multiplication inside the argument. If we subtract, that's the same as division on the inside of the argument. Subtract on the outside is division on the inside. This is how I say this. Exponent on the inside is multiplication by that number on the outside. This is an extremely useful one for logarithmic differentiation and L'Hopital's rule, the exponential indeterminate forms. And this one is good for taking the derivative of all logarithmic functions. You can essentially take the derivative of log x and get it this way. Also, I checked number 1. How we're going to use the log laws are slightly different. If they give us log base 12 of 3 and log base 12 of 48 and add, I don't know how to compute either of these guys specifically, because we're looking for, what this asks us is, what do I raise 12 to get the number 3? Some weird exponent, I have no idea what it is. But if we combine them using property 1 and multiply them, 3 times 48 is 144. 144 is 12 squared. As soon as I have this, we have like the cancellation law. And that says that we're going to have 2. So log base 12 of 3 plus log base 12 of 48 is equal to 2. Now let's do the hyperbolic functions, which are linear combinations of our magic guy, the exponential function e to the x. All right, for the hyperbolic functions and their inverses, first of all, let's talk about the special magic exponential function e to the x. E is the number which is defined. E is approximately equal to 2.71828 ... to a few decimal places. And what this number is the number such that the limit as h approaches 0 of e to the h minus 1 over h is exactly the number 1. The slope of the tangent lines in calculus 114 or calculus 1. Once we do this, by the definition of derivative, if this is the number, the derivative of e to the x is going to be, by definition, this guy. I use the exponent law that we just talked about to get this expression. I can now factor e to the x out of both of these guys and take it outside of the limit, because the limit is h. This limit is 1, so we get e to the x times 1, which is itself. So the derivative of e to the x is itself. This is the only function which its instantaneous rate of change at that point is the value of the function at the same point. We call the inverse of this exponential function e to the x the natural logarithm and denote it ln x. So ln x is log base e of x. And this is what they look like. This is the magic function which we're going to use all the time. How does this relate to hyperbolic functions? Hyperbolic functions, the sine hyperbolic and cos hyperbolic, are essentially the even and odd part of the exponential function. Let's check that out. All right, for the hyperbolic functions and their inverses, we're going to have to define even and odd functions quickly. So a function is even if f of negative x equals f of x, therefore it's symmetric with respect to the y-axis. A function is odd if f of negative x equals negative f of x, and that's as we've reflected about the x-axis, the y-axis, and then the x-axis, or we're symmetric with respect to the origin in this case. And if you have neither, that means you're not symmetric with respect to the origin or the y-axis. Then we're going to have theorem, which I forgot. Theorem. Let f of x be a function with 0 in the domain, so we can talk about whether it's even or odd or neither. Then there are functions fo of x, or odd part, which is f of x minus f of negative x over 2, and f even, which is f of x plus f of negative x over 2, such that fo is an odd function and fe is an even function respectively, and we have that f is the sum of an odd and even function always. What are we going to do with this business? We're going to play this game. Let's prove that, and then we'll play this game with the function e to the x and see what happens, and we'll get the definition of sine hyperbolic and cos hyperbolic. All right, proof. So first of all, what we're going to do is we're going to show what they said. F of x, and I'm going to use my two favorite tricks, which are the dirty math tricks. I'm going to multiply by 1, and I'm going to add 0. So f of x is actually, we can multiply by 2 over 2. Clever. And then on the top, what I can do is I can write that as f of x plus f of x over 2. I just took two f of x's and turned it into a sum. And then what I'm going to do is this is multiplying by 1. And then I'm going to add 0. I'm going to add f of x plus f of x. And then we're going to add 0. So plus f of negative x minus f of negative x over 2. And that right there is 0. So then what I get from that is I'm going to get, this says that f of x is equal to f of x, let's regroup, minus f of negative x over 2 plus f of x plus f of negative x over 2, which is fo of x by definition plus fe of x by definition in my theorem. So I can write f as this weird linear combination of fo and fe. Then what we want to do is, for odd, fo should be odd. So fo of negative x is equal to, here's fo, so this should be f of negative x minus f of negative x over 2, which is f of negative x minus f of x over 2. The negative's in the wrong spot, so pull a negative out of that. That's negative f of x minus f of negative x over 2, which is negative f0 of x. Therefore, this says that fo is odd. As an exercise, you can check that this guy is actually an even function. Put negative in there and you'll get fe of x again. Therefore, we have the result. You can check as the viewer that fe is actually even. Why does this help us? Well, what we're going to do now is, let's erase this quickly. So now we have example 2, we can find the even and odd part of e to the x. What happens when we do that? Well, fo of x is going to be f of x minus f of negative x over 2, which is e to the x minus e to the negative x over 2. And this is what we're going to define as sine hyperbolic x. And fe of x is equal to f of x plus f of negative x over 2, which is going to be e to the x plus e to the negative x over 2, which is going to be our definition of cosine hyperbolic x. This is the definition of sine hyperbolic and cosine hyperbolic. And it happens to be the odd part and the even part of e to the x. Therefore, our first hyperbolic identity is in fact e to the x equals sine hyperbolic x plus cos hyperbolic x. It is the even and odd part. This is the odd part, this is the even part of e to the x. So this is the definition of sine hyperbolic and cosine hyperbolic. Again, I said I would focus on these ones. Tan hyperbolic is going to be sine hyperbolic x over cosine hyperbolic x, which if you simplify it will cancel the 2's, and we're going to get e to the x minus e to the negative x over e to the x plus e to the negative x. This is sine hyperbolic, cosine hyperbolic, and tan hyperbolic. And remember, sine hyperbolic and cosine hyperbolic are the odd and even part of e to the x respectively. What do they look like graphically? Sine hyperbolic is going to be this guy. Cosine hyperbolic is going to look like this right at 1. And tan hyperbolic is going to have 1 and minus 1 as horizontal asymptotes, and we're going to do this. This will be tan hyperbolic x. So these are the three main hyperbolic functions: sine hyperbolic, cosine hyperbolic, and tan hyperbolic. These two are linear combinations of the exponential function e to the x, and these ones are combinations, or the ratio of sine hyperbolic over cosine hyperbolic. These are their graphs. Now what we'll do in the last part of this is give the inverses of the hyperbolic functions: sine hyperbolic inverse, cosine hyperbolic inverse, and tan hyperbolic inverse. Let's look at those. And in particular, this one isn't one-to-one, so we're going to restrict. These are the functions that we're going to now invert and find inverses for. Let's do that. All right, to finish off, these are the hyperbolic functions: sine hyperbolic, cos hyperbolic, and tan hyperbolic, together with their inverses. First of all, we should notice that sine hyperbolic is defined, has domain and range R, so does the inverse. And we have these clever formulas. We can solve algebraically for sine hyperbolic inverse, cos hyperbolic inverse, and tan hyperbolic inverse, and we can get an explicit formula for their inverse expressions. Natural logarithm of x plus the square root of x squared plus 1 for sine hyperbolic, and these similar identities for cos hyperbolic inverse and tan hyperbolic inverse. This is essentially the main three types. Of course, there are the cosecant hyperbolic, secant hyperbolic, and cotan hyperbolic functions and their inverse as well. But as I said, we will stick to in the trigonometric and the hyperbolic cases, we will stick to sine, cosine, and tangent and focus on those guys. We also have, obviously, the cancellation laws. These guys cancel each other in their respective domains. And we have trigonometric identities similar to hyperbolic identities. The main one you want to start with is cos hyperbolic squared x minus sine hyperbolic squared x equals 1. This is because we're on the hyperbola x squared minus y squared equals 1, so that shouldn't be a surprise to us if we think about this. But for any angle x, cos hyperbolic squared x, not really angle for any real number now, cos hyperbolic squared x minus sine hyperbolic squared x is always equal to 1, and we can derive a bunch of other identities similar to the trigonometric identities for the hyperbolic functions. Please subscribe right here. I will see you next time.